We're in the Starrag HQ here in Kentucky, and I'm standing here with Jim. We're going to be talking about semiconductors because, man, there's so much buzz out there about semiconductors right now, Jim.
There is.
So, but what's even important? It's not something as a machinist I got to do. So what do people need in the semiconductor world to get good parts?
So in our world, it's all about material removal.
Yeah. Okay.
And there's a lot of machines on the market that can just rip aluminum. But there's a lot of things that also go along with that. So accuracy, rigidity, because there's surface finishes on these semiconductor parts that are absolutely critical, or the parts just don't function the way they're intended. So when you have tool blends, where one feature of the part is intersecting with another feature of the part, you have a blend area. If your machine doesn't have the accuracy or it doesn't have the rigidity to have that, I guess, geometric tolerance, then you lose that surface finish, you lose those blends. So that's why it's really, really important to have a rock solid machine and also a very accurate machine to be able to hold those surface finish and those blends. That's really one of the most critical features, because you're removing an enormous amount of material, whether the parts are small like we have here, or the parts are large like the size of this machine. You really, it all works out the same. It's all about material removal, but then being able to hit the accuracies and the surface finish requirements of those parts.
Okay, so in the case of Starrag, what are you guys doing for your machines to make that possible then?
So we start out with an extremely rigid base casting, normally cast iron, across the board on all of our equipment. The machine that we are standing in front of is one of our X Series 5-axis machines, but we also go up to extremely large gantry and portal type machines as well for semiconductor. So you have to have a rock solid foundation.
Okay.
From there, then you also have to have the motion control. So that goes back to using scales on every axis. You also have to have the control. In this case, we're using a Siemens Sinumeric 1. You have to have the motion control, but you have to have the rigid and the solid base. Okay. So you start with the foundation, you build up from there like anything else.
What about on the spindle side? Because I mean, that's part of the stability. As a machinist, I know that much at least.
So on a smaller piece of equipment like this, or for the smaller work pieces, we generally in semiconductor will go with like our 30,000 RPM spindle HSK 100. But on our larger components and larger machines, we can go up to 20,000 RPM with the HSK 100.
Up to 20,000 RPM,
20,000 RPM
on a 100?
Yes.
Seriously?
Yeah, that's what we're able to do. And what that really gives you is the best of both worlds, because you have the HSK 100 attachment, larger, heavier tooling assemblies, but longer projections, because when you're working on these monolithic type parts, there's a lot of tool projection, a lot of extensions and things like that. So really, to have that larger attachment point with an HSK 100, but also have 20,000 RPM, it's really critical for semiconductor type parts. And then again, on the smaller components like this, we can go with our 30,000 RPM spindle, HSK 63, which still gives you a super strong, super rigid connection, but you're able to get to that next tier of RPM.
So Jim, I mean, you're talking about the way that you serve the semiconductor industry, but a couple things I know as a machinist that are super important when you want accuracy that you're talking about is chip management, because man, that aluminum gets into everything, and temperature control, because when you're telling me you get 20,000 RPMs at the HSK 100 size and 30,000 at HSK 63, that's a lot of heat.
It is, absolutely. So we'll start with the thermal management or thermal controls. So to manage the temperature on the spindle, on the tables, all of the direct drive rotary tables, all of the linear axes, everything has to be temperature controlled in order to maintain that geometric accuracy that we spoke about earlier. By doing that, we have a single point chiller system on the machine that's a standalone item, and that actually handles all of the temperature management, whether it's heating or cooling. So it's not just cooling, it can heat and cool to maintain basically a 2-degree Fahrenheit window, which is necessary to produce a part like this.
Yeah, so you have that stability. You don't have to worry about warm-up cycles, everything else. You've got that unit to maintain all of your temperatures.
Correct.
What about the chip management though? I mean, aluminum chips love to float and cause
They
havoc.
do. It's that's a big challenge for everyone. And what we do to combat that is we have a centralized coolant system on the machine. So we're removing the chips with a scraper type conveyor, which tends to grab the chips that are floating on the top surface. Beyond that, then we pass it through a knoll, or what we call it, internal coolant supply that has a paper band filtration, which brings it down to about 40 micron.
Okay.
And that's good enough for cabin flushing and for flood coolant. And then beyond that, for the high pressure through spindle coolant, we filter it down through a double cartridge filter, which brings it down below 10 micron, which protects the spindle, and it also protects the rotary union in the spindle at those high speeds.
Well, and also the cutting tools too. Now you're not sandblasting your cutting tools with all your
exactly,
your
or plugging those small orifices up with aluminum chips. Correct.
Very cool.
Yep. So it's pretty impressive for us.
With all of the features on this part, you're telling me that you did it all done in one go, in one setup.
In this case, this part, for demonstration purposes, was done in 2 setups.
Okay.
We basically prepped the backside so that we had a squared up piece with good material to hold on to. And then from there, we process the rest of the part all complete in one setup. So essentially, yeah, we could say one setup for the main portion of the milling features. We did have to prep the block in the first case, but I think all in, we were right at or just under 2 hours total. And there's a lot of cavitation, a lot of intersecting points. There's a lot of material removal, even on a small workpiece like this.
Well, and everything's got such a high level finish on it, and it's got all the transitions are very smooth. There's no mismatch. There's no like gouge lines. There's no transfer.
And that goes back to what we talked about before, is having that thermal stability, having that rock solid foundation, having that motion control on the drives and everything, having the positional accuracy and things like that from the scales. All of those things go together and they harmonize. It has to be a perfect world in that case to get, again, where you're not having to have a lot of hand work and a lot of hand finishing and after hours processing once the part comes off the machine.
So they can take them apart off the machine once it's done and put it right into what they need to versus having to hand polish or finish.
That's the goal, yeah. And in this case, that's what we achieved.
Very cool. Awesome. Well, thank you, Jim.
Yeah, thank you.